Power facility are everywhere and vital. So we designed a substation inspection robot, which is a system that uses robot technology to inspect and monitor the substation, which can improve the efficiency and safety of substation inspection. We adopt a vision-based positioning and navigating method to realize the autonomous movement of the robot and the tracking of the facilities. We also designed an image analysis method based on deep learning to realize the fault diagnosis and the early warning function of the robot by identifying and locating the fault point of the substation.
Our voltage is powered by a lithium battery with a rated voltage of 16 voltage as the main power source and controlled by an STM32 microcontroller. The first branch of the power supply is connected to the DC-to-DC module, and after a voltage reduction, the sky-end power supply module is powered on. The PDZ can send the image to the sky-end. The sky-end will send the received data to the MK15 remote control remotely through UMB antenna. Users can also remotely control the shooting angle of PTZ using MK15 and send control signals to STM to control the motor rotation. MK itself has an hotspot function, and users can establish a connection with MK using their mobile phone or computer to obtain PTZ shooting images. The received image is recognized using the UV5 algorithm to detect the power equipment. In addition, we can establish a connection between the mobile phone and the Bluetooth module, send controlled instructions to the microcontroller, and then control the robot's movement. The second branch connects two voltage reduction modules and supplies power to the two L298N motor drive modules. After receiving the PWM signal from STM, it outputs the corresponding voltage to the motor. The third branch supplies power to STM and ESP through the DC-to-DC module. ESP can connect it to a local area network and establish communication with users' devices through a cloud platform. DHT can detect temperature and humidity, while MPU is a gyroscope connected to the STM through I2C.
We follow the concept development guideline to create the concept selection. There are three factors to consider: power supply, communication protocol DHT11, and the movement. We designed three different options here. Based on the safety, stability, and ease of use, we chose option 2 for our final design. The poly battery is safer and has stable voltage and are more flexible compared to the external power supply. The use of one-wire bus as a communication protocol for the DHT11 is easy to use. The ability of track to adapt the terrain is between the wheel and the bionic leg, but it is easier to install.
There are two control methods. The first method is to control the movement of robots by connecting the mobile phone to the Bluetooth module on the robot. The second way is to control the movement of the robot through the MK15 with a max control distance of 10 km. The operator can remotely control the gimbal camera's shooting angle and adjust focus from the user's interface. With temperature and humidity sensor, we can detect the temperature and humidity of environment.
And the local server we designed can make detecting the photos we get easy and fast. Just press the buttons and the photo will be downloaded from server and detected.
We designed the patch antenna array with 120 GHz frequency, and we use this simple structure to do the defect pattern test. When we change the gap of the structure from 0.5 to 1.5 millimeters, we can see the shift of the S11 plot.